Hi, and welcome to Gaffy's Grinds. In this video, we're going to be discussing the idea of what concentration means when we're talking about solutions. But before we do that, we're going to remind ourselves about what a solution is. We're going to do that by using an example. Let's look at this substance here. This substance represents table salt, or what we call sodium chloride. We've seen this before. Sodium chloride is an ionic substance, which means that it's made of these different ions connected together, and they're all held together by ionic bonds, very strong forces of attraction. Now, here you see red and green circles alternating, and these represent two different ions. We'll say that the green one represents what we call the chloride ion, and the red one represents a sodium ion. Sorry, sodium. So sodium chloride then is the name of this salt, sodium chloride. Now, we know that this substance is a solid because of the arrangement of the particles. They're all touching and they're arranged in neat rows. And together, we call this substance sodium chloride. Our everyday name for this substance is salt. So we'll just call it salt from here on out. Now, what we can do with this salt is we can take it and we can add it to some water. So here I'm drawing a container. And in that container, there is some liquid water. Okay, so liquid water. We know that that's also made of particles, but it's not ionic. It's a covalent substance, and it's in the form of molecules. We're going to take our salt and we're going to add it into the water. We say that what happens to the salt is that the salt dissolves. The salt dissolves in the water. That's the process that happens to the salt. So what does this look like after? Well, here after, I'm going to draw my container. I still have my water, and I'm not drawing the particles, but do know that it's made of particles. And what essentially has happened is that when you put the sodium chloride crystal into the water molecules are able to interact with the ions and pull them apart. So essentially, you're breaking the forces of attraction that were holding the sodium and the chloride ions together. Now notice, the sodium and chloride ions are still intact. They are not broken themselves. There are still 5 chloride ions, just like there were when it was in the crystal. They didn't get broken. What did get broken, though, was the forces that were holding them together. But once we break them forces and all them ions aren't together anymore, then it stops looking like salt. So that white crystal appearance that we see when we have solid salt disappears, and now the ions are spread and mixed around in the water. And you can't see them anymore because they're much too tiny by themselves for you to see them. So they're not together in a group, which makes them more visible anymore. So it might look like they have disappeared, but they have not disappeared. They have dissolved. Now, we're going to put a few words onto this now, okay? When we're talking about all of this stuff, we say that this here, we have made a mixture. But mixture isn't really an accurate enough name for this because there's lots of different kinds of mixtures. This is a very specific kind of mixture where we have taken one substance and dissolved it into another substance to make this mixture. So here are some words that we need to know. First of all, the salt. Well, this is the thing that dissolved in this case, in this mixture. This is the thing that got dissolved. And the thing that got dissolved is known as a solute. Solutes are things that gets dissolved. Salt is an example of a solute then. Another example of a solute might be sugar. If you put sugar in water, it's also a solute when we put it in water. So salt is a solute. Water, in this case, this is the substance that did the dissolving. This dissolved the other thing. So the substance that does the dissolving, and it's often a liquid, it's usually a liquid when we're talking about these types of mixtures, but it can be other substance. It doesn't have to be a liquid, but think of it in simple terms of mostly a liquid. This substance is known as the solvent. So the solvent is the substance that does the dissolving. Okay, so water is the solvent. And again, there are other types of solvents. For example, nail varnish remover. It dissolves nail varnish. So it's a solvent for nail varnish. Okay, so that's nail varnish remover. So you can see there's not only one type of solvent, but water happens to be a very good solvent. So solvent plus solute, then when we add these two things together, we get this mixture over here. And the name for this here is we call the mixture a solution. Solutions are mixtures of solutes and solvents. That's what a mixture, that's what a solution is. Now that we understand the concept and we've reminded ourselves of the concept of solutions, how they work, let's just quickly clarify and make a list of what things that are solutions and things that are not solutions. Okay, so here I'm making a quick table. I'm going to put things that are solutions over here, and put things that are not solutions over here. Sorry, I should say not solutions. Now, first of all, we've seen one already for sure. We've got salt plus water. That's definitely a solution. And we say it's a solution because it does work. It does dissolve. The salt does dissolve in water. So if something dissolves in water, then we can call it a solution. Or if something dissolves into the solvent, it is a solution. Another example of a solution would be sugar and water. All of our fizzy drinks rely on this fact. Those nice, sweet, fizzy drinks, if there was no sugar in them, then they wouldn't taste very good. Also, if anyone puts sugar in your tea or your coffee, then that's exactly what you're doing. You're dissolving sugar in water to make it sweeter. Also, coffee granules in that case, when you're making coffee or tea leaves, the different chemicals in there, they dissolve in water too. So they're all solutions. Let's see though what's an example of something is not a solution. Some of you may have done the dishes before after dinner and realized that if you leave the dishes in the sink for a while, any oils that were on your plate from the cooking, they sit and they float on top of the water. They don't actually mix and dissolve in the water. They'll float in this like layer on top. So oil plus water is an example of something that is not a solution. And the reason for that is the oil will not dissolve and properly mix with the water. You may have used Tipp-Ex before on your copy, or some of you may even be bold enough to use Tipp-Ex to write on the desk with. Draw some picture or write your name on the desk and got in trouble for it. Or maybe the teacher kept you in to clean your desk or something like that. It happens all the time. Now, if you try to clean that off with water, it's not going to be any good because Tipp-Ex does not dissolve in water. So Tipp-Ex plus water is not a solution. We do not make a mixture. So if you wanted to clean off the Tipp-Ex, then you need to get a different solvent. Water will not work. Let's go back to solutions again. Alcohol. Most of us are familiar with the idea of that. People drinking alcohol at the weekend. Well, you can't drink pure alcohol. It's much too strong. This is what we use for cleaning things, cleaning desks, cleaning windows, cleaning all kinds of things, hand sanitizer, all that kind of thing. It's not the same alcohol that you drink because it's much too strong. So to make alcoholic drinks, they actually have to take an alcohol and have to add water to it. Make a solution with water. So it's not 100% alcohol. In fact, most alcoholic drinks, bottles of beer, whatever you want, most of them are around only 4 or 5% alcohol. The rest is water, sugars, and flavors. Another thing, another solution, and I want to show you, point out that not, so here we have 2 solid solutes. But I want you to notice that they don't have to be. This is a liquid solute. The alcohol here is a liquid. So it mixes with water. So it doesn't have to be always a solid solute. Yes, we use the solid example over here. But it does not have to be. When you open a bottle of Coke and you hear that psst, that fizz, and you get all the bubbles, that must be something dissolved in the water that makes up Coke, because Coke is mostly water. All fizzy drinks are mostly water. There must be something dissolved in that to give it that fizz. All right, you can actually see it when you open the bottle. You can see the bubbles literally rising to the surface from the fizzy drink, and that is because there is a gas dissolved in there. So this time I'm going to have a gas solute, and that gas solute that gives fizz is called carbon dioxide. Carbon dioxide plus water is another solution, and all fizzy drinks, anything fizzy, is based on this idea here. The last one I want to point out is I want to use an example of something which is not water as the solvent, because all of our first examples here have had water, 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 and water. And I don't want people to start thinking that water is the only solvent. So we also have, if we want to get rid of your nail varnish, it's been on too long, it's time to take it off, you would get a substance called nail varnish remover. And the ingredient in there that takes off the nail varnish is called acetone. So I wanted to show you that there are different solvents too. So water won't take off your nail varnish, but acetone will. So to make a solution of your nail varnish, you need to use acetone instead of water. So that's a different solvent. Last of all, we go over one more, go to the things which are not solutions, and we have classic example, we go to the beach. Why is there sand on the beach? Why does the water, the seawater as it comes in, not just dissolve it? Well, the answer is sand is not able to make a solution with water. So sand plus water is not a solution. Now you can put sand into water. If you took a little glass or a beaker and you put some sand in there, by all means you can put it in and stir it, and it might just float around for a minute, but then it's all going to fall to the bottom. It's not going to dissolve. It's not going to make a solution. Right, so hopefully we're very firm on the idea now of what a solution is, and we are ready to have a go at some of these questions. All right, so I want you to pause the video and work your way through these. All right, so notice the last question there. If you're not sure what you have to do there, number 4, you actually have to use these sentences as the start of your sentence. So salt mixes with water because, and then I want you to explain why does salt mix with water. So you have to finish off the sentence with something that makes sense. All right. I'm just having a quick look here. I think all of them are pretty straightforward. The last one you might have to have a good think about, but that's what they're for. That's what they're actually designed for, is to really make you think hard and trying to find something, put it into your own words, things that make sense. So don't just skip that one because it looks hard. All right. So now that we fully understand again what a solution is, we're ready to discuss the idea of concentration. Now, as always in these videos, we're going to build it up bit by bit. So we're going to start by looking at the diagram that I have here. So it says here, we're talking about concentration now, by the way, concentration. And we're not going to really explain too much what that means until we actually use examples to work through it. So it says to consider this diagram. So you've got two boxes, A and B. If the red particles represent a solute, which box has a larger quantity of solute? Pretty straightforward, but what I want you to do now is go ahead, pause the video and write down which of these you think has a larger quantity of solute. All right, I'm hoping that this is a pretty straightforward idea. Basically, the more particles, the higher the quantity. Should make sense. So if the red particles are the solute, which one is a higher quantity? It's got to be A. So I'm hoping that you said A has a higher quantity of solute. A. Now, if we were measuring the quantity of solute, in other words, how much of something we had, so especially if it was something like salt, what different ways would we have of measuring and talking about the quantities of solute? Think about the things we've learned, especially in the last booklet that we did when we talked to, I won't say what we talked about because I'll give you the answer. I want to think about this and write down 2 ways, 2 units you could use to express the quantity of a solute, the quantity of salt that was put into water. Pause the video and do that now. Okay, so here what I was hoping you were thinking about is that if you wanted to measure the amount of salt you were putting into a solution, you could first of all measure the number of grams. So grams is a way of measuring the quantity of solute. Another way you could do it, I'm hoping that you wrote down 2. If you didn't write down 2, hopefully pause the video and write down the other one now. All right, so we can talk about grams of solute, grams of salt, grams of sugar, etc. Or we could talk about moles of solute. If we had a hell of a lot of solute, too much to talk about in terms of grams, too many grams, we might start to talk about number of moles of solute. Equally, if we had a very, very, very tiny number of grams, then it's not very helpful to talk about the number of grams. If it was 6.0, if it was 6.4 by 10 to the minus 8 grams, that's not really a useful amount of grams. So it might make more sense to talk about the number of moles instead. All right, so that was a quick recap and seeing straight away how can our idea of stoichiometry and moles linked to quantities of solute. All right, on to the next bit. Consider the diagram. Imagine that each represents a container full of water. So we have two containers, C and D. I'll let you take a close look at the picture and think about what you can figure out from just looking at the picture. All right. So at this stage now, I want you to think about these three statements and write down which one describes the diagram the best. Pause the video, do that now. All right, so looking at the three statements, let's look at why some of them might be wrong. So hopefully you got the idea that the size of the box is supposed to represent the volume. So let's look at part one. It says C and D have the same volume of solvent. Now, unless there's something extraordinary going on, now I know this is in 2D, so volume is in 3D, but it's very hard for me to draw that. So I just did it in 2D. This is something really weird going on in the third dimension behind the computer screen, where it goes back into the screen. Unless there's something very weird going on, then we could definitely assume that D is a bigger box or bigger container than C. Hopefully you got that. That was my idea. That was what I was trying to show. And that definitely then the first one has to be wrong. C and D do not have the same volume if D is a much bigger box than C and they're both full. So we can rule out number one. Number two, D has a higher volume of solvent than C. Now that to me sounds right because D is a bigger box. D is full and D is full of solvent. C is also full, but it's a smaller box. Therefore, it has to have a smaller volume. So for me, this one here best describes the situation. Let's just rule out the last one. C has a higher volume of solvent than D. Well, this is the complete opposite of number two. And hopefully to you, it very obviously is incorrect because C is a much smaller box. Therefore, D has to have more volume. Okay, so remember when we're talking about volume, we're talking about the amount of space taken up. And when we're talking about volumes in solutions, then we're talking about usually the volume of the solution. So how much does the mixture, or how much does the liquid take up? Well, how much space does it take up? And in this case, it's taken up the full of the box of C, the full of the box of D. So therefore, if it's taken up the full of the box of D, D is a much bigger box, then the volume has to be higher. All right. Let me just think. Yeah, okay. So let's put these two ideas together. When we make solutions, we are often interested to know both of these things together. So this thing up here that we learned here, how much quantity of solute do we have? So has a larger quantity. Quantity just refers to how many grams or how many moles you have, how much of it is there. But we also need to consider the volume as well, okay? So when we make solutions, we are often interested to know how much solute is dissolved in a specific amount of the solution. And we call this the concentration. So when we compare solutions, it's usually a good idea to compare them based on a similar or equal volume. So let's say this one, sorry. Let's say I'm going to put ink to shape on this for a second here. I'm going to draw a volume. So there's a box. I'm going to copy that box so I know it's the exact same size. Okay. So we've got two solutions, two containers here. And the important thing to think about is that these have an equal volume. Equal volume means that it's the same amount of solution in them. Okay. Now, sorry, I'm going to have to pause the video for 1 second. Okay, so let's assume here that these are full of water. So I am going to fill them in here with a blue liquid to represent water. And the boxes are the same size. So we're going to say Now, it doesn't always have to be a specific volume, but usually when we're talking about solutions, we would refer to a specific volume. Okay, so here's two boxes equal size. And we're going to say, let's set that the volume is exactly 1 liter of solution. So both of these are 1 liter. And because they're about 1 liter, we can kind of compare them equally. So we say that 1 liter is the given volume. 1 liter is the given volume. Now, it doesn't always have to be 1 liter, but you have to be given a volume so you can compare things, the concentration of two things. Now, let's say in the first box, we have a red solute, which looks like this. 1, 3, 4. There are 4 particles of the solute. Now, that's not very realistic. We know in most more than 4, but we're trying to keep it simple here. In the second box, it's the same solute. This time there are many more particles. So how might we express this and show that these are different? The first thing to think about is, well, how much of the solute is there? In this case, we say that there are 4 particles. 4 particles for every 1 liter of solution. 4 particles per 1 liter. So we're talking about the quantity of solute in a given volume in 1 liter of the solution. The second one, we can talk about 1, 2, 3, 4, 5, 6, 7. Sorry, I have to start again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 particles for every 1 liter. Okay, so that's how we might express these things and compare them. So obviously then we would say that the second container has more particles for every liter or for the given volume. More particles for the same given volume. So in this case, we would say that this one has a higher concentration. This one has a lower concentration. So the next level of thinking then is we don't usually measure the number of particles in the solution. Usually we will instead measure the number of grams or moles. So it would be grams per liter or grams per 100 centimeters cubed, whatever the given volume is, will be grams or moles per that volume, per that given volume. So hopefully that idea of concentration, you have it now. Let's think about, or let's have a look at what the official definition of this is. Concentration, the amount of solute in a specified amount of solution. So you're given a specific amount or volume of solution, 1 liter, 2 liters, could be 10 liters, could be less than a liter, could be 0.1 liter, but you're given a specified amount, and then you're also given the quantity of the solute that's in there. All right, so that's in red. So what I want you to do is I want you to write that down for me. Pause your video and write this down in your dictionary. And then let's have a look at the next question. Consider the following diagram and answer the question. So have a study of E and F there, the 2 diagrams. All right, I want you to pause the video now and have a go at them questions. I'm pretty sure those are pretty straightforward for you guys now. Those are pretty straightforward. We go through them in class when we're back. There's one more idea I want to get across to you today, and that is this. Imagine for a second that we have 2 glasses of orange squash. So my body or whatever brand of orange squash you drink, that's fine. Okay, and they're orange, so I'm going to get an orange marker. Okay, and have to go with this and see what it looks like. So this is the first one. Okay, so this is the first one. And the idea that I'm trying to get across to you is that this is quite dark in color. It's quite orange. Okay. This is the second one. And here you can see, hopefully, it's less dark in color. So we all know what that nice maiwadi tastes like. It tastes like this one on the left. That nice dark color. Sometimes it can kind of seem like maybe you put too much in, but no. No one wants that maiwadi that looks like maiwadi but doesn't taste like it. All right. So how did you make this maiwadi? In the first case, what you did is you took your glass, you put in quite a lot of what we call the original maiwadi from the bottle, and this is very dark. Quite a lot of that. And to it, you added some water to make your solution. Ooh, sorry, I need to fix that marker. It's way too thick. Okay, so to this, you added a little bit of water. So you added quite a lot of the original maiwadi from the bottle, what we call the concentrated maiwadi. You added quite a lot of that for a reasonably small amount of water. In the second case, how you made it is you took a glass and you took a very small amount of the concentrate compared to the amount of water you added. So here's your H2O. And that's how you would get the two different results. Now, in this case, on the left, we say that this is a very concentrated, or this is a more concentrated glass of maiwadi. More concentrated. Because you have a larger amount of the solute, we'll call this the solute for now, for the amount of solvent. You have a large amount of solute for the amount of solvent, which means that the solution will be more concentrated. In this case, you have a smaller amount of solute for a larger amount of solvent. And the result is a less concentrated solution. Less concentrated. Another way that people talk about this is they say that it's more dilute. More dilute. All right, so they're kind of the opposite of each other. Something is either concentrated or it's dilute. Okay, they can't be both. So concentrated or dilute. All right, so that is the difference then between a high concentrated solution or a more concentrated solution and a less concentrated solution. The big idea here is that more concentrated solutions have more solute for the volume of solvent, whereas in a less concentrated solution, they have less solute for that volume of solvent. Okay, so that is the idea of concentrated solutions and dilute solutions or less concentrated solutions. I'm hoping that that makes sense. We've used a concrete example to explain the idea of more concentrated and less concentrated. And now, again, we have a couple of things for you to make a note of here for me. Okay, so what I want you to do is I want you to pause the video and I want you to write down the two explanations or definitions here in your keyword dictionary. Pause the video and do that for me now. Okay, in the next video, we're going to come back to these two ideas, concentrated and dilute solutions, and we're going to look at how can we work out or calculate the concentration of solutions. Okay, all right, guys. So I hope you have enjoyed and learned a lot from that reintroduction to what a solution is, and from reintroduction to what a solution is, the idea that solutions can have different amounts of solutes dissolve and different amounts of solvent, and big new ideas that we learned about how something can be more concentrated or less concentrated, and that's just determined by how much the solute is there. Okay, so if we were to link the two ideas together then that we learned about, then this here is the higher concentration, that is that one there, so it's just got more particles for the amount of solute, or more grams or more moles, however you want to measure it. Whereas this one here has less particles for the same amount of solution. Okay, so that would be less concentrated or more dilute. All right, guys, that is the first video in this. In the next one, like I said, in the next lesson, we are going to learn about how to discuss the different ways we can talk about concentration. All right, that's it, guys. See you in the next video.